we're going to find resultant vectors in 3 space. So algebraically, instead of drawing this, because drawing this would be pretty difficult. They've given this vector. This is a vector in 3 space. It's a positional vector, right? It's starting at the origin and going to these 3 points. So, maybe it does something like this. This is another positional vector. This is another positional vector. We are taking them, so moving this guy over, moving this guy over, and finding what the new positional vector is in 3 space. Okay? And instead of trying to do that graphically, we're going to do it algebraically. So actually putting out our numbers here. And we'll do it 2 different ways. This is component form. These are the components of the vector, all right? The coordinates. You can call it the coordinate form. We're going to do it with coordinates, and we're going to do it using unit vectors. So using component form, these are scalars. We have a scalar of 2, scalar of -1/2, and a scalar of 3 that we have to multiply each of these vectors by. Okay? And I should put these on top. So in component form, the way I'm going to rewrite this is we're going to have 2 multiplied by 2, -4, 1, minus -1/2 multiplied by -8, 6, -2, and plus 3 multiplied by 7, 11, and 12. Okay. We're going to get these 3 components, so we'll have our 3 components all together. This component here will be left at, so this is our first vector, 2, -4. Oh my gosh, no it's not. Let's do some multiplication. We have to distribute these numbers. I'm not sure why I just repeated them. And we'll have to do that for all 3 of these processes, okay? So we'll end up with 4, -8, and 2. This vector here will be left with, some commas here, +4, -3, and +1. And in our last set, we'll be left with 21, 33, and 36. Okay. So we have these all here, and these are positive values. Now these are all of the x values, these are all of the y values, and these are all of the z values. We're going to combine them all. So we have z1, z2, and z3. So the idea now becomes we have one large component, and we'll do x1 plus x2 plus x3, y1 plus y2 plus y3, and z1 plus z2 plus z3. Okay? And I didn't order them, but the numbers are essentially what order they're in. So we have 4 plus 4 plus 21. Our y's are -8 minus 3 plus 33. And our z's are 2 plus 1 plus 36. Okay. Oh no, too much. We're going to simplify this, and it'll give us our new equivalent positional vector. This is 8, 9, 29, 11, 22, and 39. Is that right, guys? I think so. Okay, so this would be the new equivalent positional vector, at least the components of it. Another way we could have gone about doing this, okay, is changing each of these, the beginning part, into unit vectors. Okay, so I'm going to copy them and put them on another page very quickly here. So copy. Go to a new page. There we go. Okay. So we're going to put them into their unit vector form. Okay. And remember the question said 2x minus ½ vector y plus 3 vector z. Okay. So our first one, our first vector here, we have a scalar of 2, and its unit vectors are 2i minus 4j plus k minus 1/2 negative 8i plus 6j minus 2k, and finally plus 3 times 7i plus 11j plus 12k. So this way we're all in unit vectors, and we can actually combine them right off the bat. We didn't have to wait till they're in their components and then add them up together. So now we use our distributive property 2 goes into all 3 of these, and same with the other scalars. And we'll have new values for our unit vectors. We'll have 4i minus 8j plus 2k plus 4i minus 3j plus k plus 21i plus 33j plus 36k. Once we've done that, we collect our like terms. These are our i's, our j's, and our k's. And we put them all together to find the unit vectors. So 4 and 4 is 8 plus 21 is 29 vector I. Forgot to put the vector there. Negative 11, 22 vector j. And I think it becomes 39, right? Negative, oh, wait, isn't that right? K3, yep. 39 vector k. So if we look at both pages, we've got the same answer twice. We just did them 2 different ways, one in component form and one using unit vectors.